Welcome to Lecture 4.4, Solving 2x2 Homogeneous Systems of ODEs. So we're going to start with a simple example, something that we can actually solve by inspection, so we can see some patterns and develop some intuition. Then we're going to state a more general theory, and I'll actually show you why it's true. And then we're going to revisit our 2x2 system that we derived last lecture when we were studying that mixing tank problem. Okay, so let's begin. Okay, so let's consider the following homogeneous system. Now, let's write this in standard, I don't want to say standard notation, let's say elementary notation. So this is all this system says. So x1 of 0 equals 2, and x2 of 0 equals 3. And though this is a system, it's really just two separate ODEs, one for x1 and one for x2. And this is easy. This is something that both of these ODEs are exponential to k, so the solution is c e to the kt, and this is the value of c. So the general solution is, how do I want to say this? Say it down here. The general solution is that x1 of t equals ce to the negative t, and x2 of t equals I should probably say c1 and call this c2 e to the negative 4t. Okay, so now it's not hard to see that c1 equals 2 and c2 equals 3. That's just these two. But let me actually take a moment to write this back in vector notation. So in vector notation, this is x, of course, is this thing. So x is c1 e to the negative t on top, and c2 e to the negative 4t on the bottom. And sorry, that should be a 4t. It sort of looks like it. And now let me show you something. Let me write this as, you may not see why I'm doing this, but you'll see shortly. Well, I certainly don't have to, but I want to show you some intuition. So e to the negative, so I can split this up into two parts, one of them involving c1 and one of them involving c2. So I'm going to write this as c1 times something plus c2 times something else. So this first something is e to the negative t and 0, and this second something is 0 e to the negative 4t. Let's make that negative sign bigger. So I can actually write this as c1 e to the negative t times 1, 0 plus c2 e to the negative 4t times 0, 1. And I wanted to do this, so this is the general solution. And I wanted to do this before I actually plugged in 2 and 3, so you can see where these things actually come from. So let's plug in our initial conditions, and you know where this is going. So plug in the initial condition. So I should say that this up here is x of t, just to make that clear. So x of 0 is, so let's plug in 0 into this. We get c1, this is 1, so we get c1 times 1, 0 plus c2 times 0, 1, and we set that equal to our initial vector, 2, 3. So it's easy to see that, something you already knew, that c1 equals 2 and c3 equals 3. So one thing that I want to show you, so I'm going to say this is call this a remark. So this matrix here, the eigenvalues are -1 and -4. This is pretty easy to see. If you haven't dealt with eigenvalues, eigenvectors before, may not be something that you guess, and that's fine. You can use our old method to find them. But it's not hard to see that the eigenvectors, the eigenvalues, and eigenvectors, maybe I should call them the eigenstuff of this matrix, -1, 0, 0, -4. So you have lambda 1 equals -1 with corresponding eigenvector 1, 0. Again, it's not, notice, let's do up here, let's say -1, 0, 0, 0, -4 times 1, 0 equals -1, 0. Notice that, and also notice that -1, 0, 0, -4 times 0, 1, make that more of a 0, equals 0, -4. So this is an eigenvector with eigenvalue -1, and this is an eigenvector with eigenvalue -4. And you can see the pattern, what the eigenvalues and eigenvectors are going to be for any diagonal matrix. We could say this is diagonal because everything off the main diagonal is 0. So anyways, the eigenvalues and eigenvectors are this, and then the other one is I don't want to say V2. I want to say lambda 2 first. Lambda 2 equals -4 with V2 equals 0, 1. And now let me ask you, what do you see? Here's the general solution, and here are the eigenvalues and eigenvectors. Do you see these things appearing up here? Yep, there's a -1 right here. There's a -4 right here. These are the eigenvalues, and these are the eigenvectors. And that is not a coincidence. We started with a simple matrix that we can do by hand, so we can actually see this, but now I want to state a more general theory. Okay, so if AV equals lambda V, meaning if lambda and V are an eigenvalue-eigenvector pair, then this solves the homogeneous system x prime equals ax. Okay, so let's see why this is true. I don't want to use the word proof. That can be a little intimidating. So let's actually, well, I'm going to write down why. Okay, so why is this true? And this is easy. Just plug it in, and check. That's all you have to do. Okay, so if x equals e to the lambda t times v, let's actually write out what this is more explicitly. So v is going to have two entries in it. Well, let's write it like this. The top entry is going to be e to the lambda t times some number x1, and the bottom entry is e to the lambda t times x2. So here I'm assuming that v is just a vector. Let's call it x1, x2. So this is x, let me write this, x of t. Then what's the derivative of this? X prime of t, we just take the derivative of each entry. Well, let's do this first. So this is lambda, the top is lambda e to the lambda t times x1. Remember, x1, it's not a variable. I mean, I call it x1, but maybe I should have called this a and b. This is just a number. That's just a number. T is the variable. And this is, bottom is lambda e to the lambda t. Yeah, I really should have called this a and b. Oh well. And this, we can pull out the constant, and we can write this as, this is just lambda times this guy. I'm sorry, not, oh yeah, this guy, which is lambda times e to the lambda t times v. Okay, so the derivative of this, so I basically just plug this into the left-hand side of the equation. The derivative of this, x prime, is this thing. Let me circle it. Okay, let's plug this into the right-hand side of the equation. Let's take this, or let's take x and multiply by a. So also, a times x is a times e to the lambda t times v. Now, this is just a, well, this is just a scalar valued function, and we can pull it out in front of the matrix. We cannot change the order of operations of matrices and vectors, but this is just a function. We can certainly pull it outside, so we can write this as e to the lambda t times a times v. And now, v is an eigenvector, so I can write this as e to the lambda t times lambda times v. And look what we get. These two things are equal. That's all we had to do to show why that is. That's all we had to do to prove this statement. Next, let me make the comment that because this equation up here, this system is homogeneous, that if we have any two solutions, x1 and x2, then there's some, well, let me start writing this down. Let me use blue now. Remark is if, since a, let me erase, write it this way. Since x prime equals a x is homogeneous, then if x1 of t and x2 of t are solutions, then so is any linear combination of them. So is c1 x1, I'm going to omit the of t, plus c2 x2. And this is just you can think of this as superposition. Forgot my R. Let's try that again. Superposition. Okay, so how do we show that? Well, again, that's also not hard. If we have, so if x1 prime equals a times x1, let me write down y. If x1 prime equals ax1 and x2 prime equals ax2, then c1 x1 plus c2 x2, take the derivative of that. What do we get? Notice we get c1 x1 prime plus c2 x2 prime. And we know that x1 is just x1 prime is just ax1, and this is just ax2. So we can write this as c1 ax1 plus c2 ax2. And we can factor out the a to write this as a times cx1 plus c1 x1 plus c2 x2. And notice this so-called proof is no different than what we did with first order ODEs or second order ODEs. We said that we had two solutions, x1 and x2. We took c1 x1 plus c2 x2, plugged it in, and showed that yes, this function prime equals a times that function. Therefore, that is a solution. So here's the big theorem, the big idea of this lecture. This first thing I'm not going to prove, I'm just going to state, but it shouldn't come as no surprise. The general solution of a 2x2 system of ODEs is a two-parameter family, C1 x1 plus C2 x2 always. And naturally, if this is a 3x3 system, then there'll be a three-parameter family, and so on. Therefore, if A happens to have distinct eigenvalues, lambda 1 and lambda 2, with corresponding eigenvectors v1 and v2, notice that if these are distinct, then these things better be distinct because they are scaled by a different amount, then automatically the general solution to this homogeneous equation is this right here. Because if we have these eigenvalues, then we know that's a solution. We know that's a solution, and knowing that there's a two-parameter family of solutions, that tells us that this is everything. This is the general solution. So not surprisingly, if we have an initial condition, x of 0 equals some initial vector, then that determines a unique particular solution. So having these two pieces of information, the A and the B, that is enough to determine C1 and C2. And you can imagine why that is because when you plug in 0 into here, these exponential functions go away and you have a 2x2 system, C1 V1 plus C2 V2, two unknowns, C1 and C2, equal to A and B, and you can solve for C1 and C2. Okay, now it's time to revisit our example from the previous lecture when we had a mixing problem with two tanks. This was our homogeneous system that we derived after changing variables from x to y, and it's easy to verify that the eigenvalues and eigenvectors of this matrix are these things here. Generally, I want you to do these by hand, but if there's nasty fractions or decimals like this, I think it's fine to use a computer, which is honestly what I did. So the first thing to do is write down the general solution, and we know this. Our big theorem says once we have the eigenvalues and eigenvectors, we're done. So the general solution is y of t equals c1 e to the negative 0.25t times 1 negative 2 plus c2 e to the negative 0.5, 0.05 t times 3/2. So this is the general solution. That's it. So let's plug in our initial condition, 13, negative 10. So let's plug in the initial condition. So y of 0 equals C1. Now, plugging in 0 is going to make this whole thing 1, and it's going to make that whole thing 1. So it's going to be C1 times 1 negative 2 plus C2 times 3 positive 2. And we set that equal to 13 and negative 10. So this gives us a system. C1 plus 3C2 equals 13. Negative 2C1 plus 2C2 equals negative 10. That's the old way to write it. Or, of course, if you want to write this in matrix notation, it's 1, 3, negative 2, 2. I'm just copying these 4 entries into here. And times C1, C2 equals 13, negative 10. I don't care which, at this point I don't care how you solve this. It's a 2x2 system, so solve it however you want to. And when you do, you get that C1 equals 7 and C2 equals 2. So that means our particular solution that satisfies this initial condition. Let's write that. Our particular solution that satisfies the initial condition is y of t equals 7. Oh, I'm sorry, I already almost wrote C1. 7 times e to the negative 0.25 t times 1 negative 2 plus 2 times, I did it again almost, did something different that time, 2 times e to the negative 0.05 t times 3, 2. So this is our particular solution. And let me just mention what another way to write this. I'm not going to. I like writing it like this better, but this vector form may make it a little confusing sometimes, but remember, you can always just multiply this thing inside of that vector if you want to, and you can multiply this inside of that vector, and then you have two vectors, and you can just add those up. So if you do that, what you get is, let's write it like this. That just means, so y of t is just y1 of t and y2 of t. That's all that is. And this is equal to, so the top is, I'm going to write this times 1 plus this times 3 on top. And then on the bottom, it's going to be this times negative 2 plus this times positive 2. So 7 times e to the negative 0.25 t plus 2 times 3 is going to give me 6, so that's plus 6 e to the, try that again, e to the negative 0.05 t. It's on top, and then on bottom, it's going to be negative 14 e to the negative 0.25 t. I think you can see what that is, right? Sorry about that. Plus 4, again that 4 is down here, 2 times 2, 4 e to the negative 0.05 t. Okay? So these are two different ways to write it. So literally y1 of t is this function and y2 of t is this function. I personally think it's a little bit cleaner to write it like this, and if you do that, it's going to make things easier later because these are the eigenvectors, and those are going to have significance when we actually plot these solutions. Okay, so we have a system of differential equations, and we found the general solution first. It looks something like this. And then we plug this in to get our particular solution that satisfied this initial condition. What we're going to do now is we're going to plot this two-parameter family of solutions on one single set of axes. Sounds like almost too hard to believe, almost too much to ask, but that's what we're going to do. Okay, so this is going to be called the phase portrait. It's going to be the plot y2 of t minus y1 of t. And so you can think of this. Let me draw this now. So that this is going to be y1 and this is going to be y2. And you can think of y1 as, it's going back to our mixing problem. This is the amount of salt in tank A, not the amount of salt, but the amount of salt above the equilibrium, which is 0, 0. So this is going to be the equilibrium salt content in both tanks. And y2 is going to represent how much salt is in tank B beyond equilibrium. So it should make sense that no matter where we start out, so suppose at time equals 0 we start out right here, and then as time goes on, we are going to approach the origin 0, 0 along some sort of curve, and that curve is going to represent at any point in time our salt content in tank A and tank B relative to equilibrium, and also how we get there. Okay, so to do this, I'm going to write this as C1 y1, and this is vector y1 of t, plus C2 y2 of t. In other words, y1 is this function, or vector y1, and vector y2 is this function. Okay, so how are we possibly going to plot all of these solutions on a single set of axes? So what we're going to do is we're going to do some easy cases first, and then we'll sort of fill in the gaps. So first of all, let's set C2 equal to 0, which kills off this term, and still leaves us with a one-parameter family of solutions, namely vector y1 of t times C1, and let's plot those, and then let's set C1 equal to 0 and plot these guys. So let's write that down. Okay, so how do we want to start? Let's set C2 equal to 0. If we do that, then y of t equals C1 y1 of t, and that is, let's write that out, that's going to be C1 e to the negative 0.2, I'm going to omit my 0.25, just write it as 0.25 t, and oh no, it shouldn't be c, it should be, got to be careful here, it's negative 2 C1 e to the negative 0.25 t. Okay, so this is my y1 and this is my y2. Again, so y2 is the height and y1 is the x-axis. Okay, so notice, let's write that down. So the y1 value on this curve. So this is the curve. Oh, let me put a vector on here. So this is the curve that we want to plot, and this curve has a y1 value and a y2 value. The y1 value is C1 e to the negative 0.25 t, and the y2 value at any time t is negative 2 C1 e to the negative 0.25 t. What I want you to notice here is the slope of this curve, y2 minus y1. So the curve y of t, which is C1 y1 of t, has slope. So it's y2 over y1, let's write that down, y2 over y1, which is negative 2. So in other words, so i.e., it lies on the line, make sure I say this right, y2 equals negative 2 y1. So it lies on this line. The line's supposed to have slope 2 that goes through the origin, so this is y2 equals negative 2 y1. So that is an important point, that when C2 equals 0, so the one parameter family of solutions when C2 is equal to 0 all lie on this line, y2 over y1 equals 0. So in other words, if we start right, suppose we start right here at time equals 0 and then time increases, we're going to be diving toward the origin, or going toward equilibrium. Now I haven't actually shown that mathematically, but our intuition says that we will be moving toward the origin. And if we start over here, our intuition says that we will move toward a steady state solution, which is 0, 0. Okay, so now let me set C2 equal to 0. I'm going to set, oh, I forgot I had this on blue. It's okay. C2 equal to 0. No, I'm sorry, not C2 equal to 0. Let me set C1 equal to 0. Yeah, I'm just going to switch colors while I'm at it. So I'm going to set C1 equal to 0. And if I do that, y of t is c2 y2 of t, which is 3 c2 e to the negative 0.05t and 2 c2 e to the negative 0.05t. So when C1 equals 0, we have a one-parameter family of solutions, and let's do the same thing. So the slope of this curve is y2 over y1, which is that over that, so which is 2 over 3. So this is going to be 2 thirds, i.e. y of t lies on the line y2 equals 2 thirds y1. So that's going to be a line that looks something like this. It's slope slightly less than 1. So this is going to be y2 equals 2 thirds y1. So I claim that if we start up here somewhere for time equals 0, and then as time goes on, we're going to be diving toward the origin, toward our steady state solution. And again, I've not shown that mathematically. Actually, let's do that right now. So let's think how I want to organize this. So up here, let's do this. So note that if I take the limit as t goes to infinity of y1 of t, so this that's right. So this is the limit as t goes to infinity of e to the negative 0.25t times the vector 1, negative 2. I'm going to get the vector 0, 0. Because as you put in larger and larger values for t, this scalar function goes to 0 and approaches 0, 0. In other words, that shows you that if you start on this line, which is where y1 is, and as time gets larger and larger, we go through the origin. So I'm going to denote that like an arrow there and an arrow there. And similarly, if you take the limit as t goes to infinity of y2 of t, that's also going to be 0, 0. In other words, if you plug in, as t gets larger and larger over here, this vector times the scalar function, this whole thing is going to go to the zero the zero vector, or the origin. So I'm going to denote this like this. Okay, so to summarize, if we're on this line at time equals 0, and then as time goes on, we go toward the origin. If we're up here, we move toward the origin, and so forth. So here's a question. What if we start up here? We're going to go to the origin, but do we do it in a straight line, or do we sort of bend this way, or do we bend that way, or what? So how do we figure this out? So I claim that this function, y1, goes to 0 faster than this function. What do I mean by faster? So, so this exponential here goes to 0 faster than this exponential over here. And to see that, plug in t equals 4. When t equals 4, we have e to the negative 1 over here, and we only have e to the negative 0.2 over here. So this thing dies out faster than this, which means curves along this line go into the origin faster than curves along this line. So here's my little personal thing, how I like to do this. I denote that by putting multiple arrows over here. And now I like to picture this plane as like a bowl. This is the bottom of the bowl, and these things are curves that are going down. So think of this like a hill. This, if you go along here, if you put a ball here and you let go, it's going to roll toward the bottom of the hill. And similarly, if you put a ball here and let go, it's going to roll toward the bottom of the hill, but this is steeper. So this hill is a lot steeper than that hill. So let me ask you, just appealing to your physical intuition, what happens if I drop a ball right here? So in this direction, the hill is steeper than it is in this direction. So what's going to happen is it's going to fall the steepest place first, and it's going to bend and do something like that. So if you start a ball right here, it's going to bend like that, and it's going to bend like that. So your solution curves are going to follow the bend. So remember when we did slope fields for differential equations, how I said imagine that these tick marks are like are currents in a river. Now I want you to imagine that these things are contour lines on a hill, and so when you're here, the ball's going to fall faster in this direction than it does in that direction. So it's going to curve like that. And so I'm going to finish by putting some of these lines on here. So this is a way to picture what all of the solutions to this system look like. So let me ask you, remember we had the initial condition y of 0 equals, what was it, 13 and negative 10. So how do we sketch that solution? Well, we go to 13 and negative 10. That's going to be somewhere down, that might be down here somewhere. So say this is 13 and negative 10, and we start right there, and then we move on toward the origin. I guess that's not a perfect drawing. It's never supposed to cross another function like this, and it's supposed to end up at the origin. So I didn't draw it perfectly, but I think you get the idea. So this path along here represents the salt concentration relative to equilibrium at any time t. Now finally, let me conclude this lecture by reminding you where this came from. Remember that we actually had an inhomogeneous equation. Remember we had x prime equals ax plus b, and then we had x of 0 equals, I think it was 5526. And the first thing we did is we found that the steady state solution was, I think it was 4236. So what you may want to do is you may want to plot the amount of salt, x1 and y1, rather than y1 and y2. So what is that phase portrait going to look like? In other words, what if we plot x1 versus, or x2 versus x1? Well, then our steady state solution is going to be up here, where this is 42, and this is 36. I think I sketched this last solution, and it's just going to be this thing shifted up by 44 and 32. So it's going to look like, I don't know if I can draw this very well, but so the actual solution curves are going to look something like this. And then let's draw that, and let's draw that. So that's what it's actually going to look like. And then the last thing I want to remind you is what the general solution looks like. If this is the general solution to the homogeneous equation, I don't know if I have any room here, I can squeeze it in. The general solution to the original equation is x of t equals the homogeneous solution, which was y of t, plus the steady state solution, which was, I think it was 4236. So compare that to what we have right here.